Hi, this is the Stars and Stellar Evolution vid, and this is my upside down approach, because I got you to make those videos, didn't I? Which I regret having done, because they were the worst things ever. Anyway, if you're from a year in the future, and I didn't get you to do these, yet I'm recycling this vid for time efficiency, then it's not an upside down approach at all. It's a downside up approach. Right, I think that's the same thing. Okay, so life cycles of stars. We need to know about the life cycles of stars, analysing starlight, diffraction grating, Stefan's law, Wien's displacement law, and the Hertzsprung-Russell diagram. Right, okay, so this is a little flowchart of the general life cycle of stars, starting like this, splitting a main sequence, and taking these two different paths and then potentially three different paths towards the end there. And I did that with my fingers on a screen like you could see what I was doing, but there you go. Right, so the first step is the nebula. And a nebula are basically big clouds of dust that clump together and clump and clump and clump and clump that into bigger and bigger clouds. I mean, the density is barely above vacuum, but it's still more than vacuum, and it does result in clumping in those regions, which grows in gravitational regions and gravitational prevalence, and then they'll get bigger and bigger and bigger and more gravitationally prevalent, and then you get something happen. That thing that you get happen is a protostar. So as the density of certain aspects or certain regions of a nebula grows to a certain degree, it starts to bunch up massively. As it gets more compact and bigger, it becomes even more massive and even more attractive, and so that process goes on and on and on. It gets extremely hot by the action of them being crushed together, and it's a huge area as well. Then it turns into eventually a main sequence star, and that is at the point when it gets to about 10 to the 7 Kelvin, where the pressure and temperature are sufficient to allow hydrogen nuclei to fuse, which releases vast amounts of energy once that starts to happen. Right? A star of stable size forms when the gravitational collapsing pressure is balanced by the radiation pressure of photons from the fusion reactions happening in the core. Now, that is actually momentum transfer from the photons, and there must be a lot of them to combat the bloody massive star collapsing in itself. So it just tells you about the power of fusion, really. Time taken for a star like this to form depends and varies on its size, and as little as 10 to the 4 years or 10,000 years, and as much as 10 to the 6 or a million years. During the process, some of the material that does not form into the protostar continues to orbit the star. This will eventually become planets. Cool. Right, once you become a main sequence star, you can take this path, right? You can become a red giant. Eventually, when the fusion of helium ceases in the core and the radiation pressure is unable to overcome the gravitational pressure, that results in collapse. Right, and that sudden increase in pressure can cause the outer layers to expand. So it's like going, and it falls in, increases that sudden increase in pressure, gets that extra burst of fusion, which causes a resistive push, and it eventually stabilizes at a much bigger surface area than it previously was. So it goes from being about 0.01 AU, which is an astronomical unit, to about 2 astronomical units, which is an astronomical unit is the average distance between the Sun and Earth. So it goes from being about 100th of that distance in radius to being 2 of that radius times that radius, which is massive because it would actually encompass us, obviously, and more so. The outer layers obviously have massively cooled down by the fact that that whole amount of energy is now spread up across a much larger area, so the luminosity will drop because of that. Eventually, the outer layers will shed off, and it will leave that core, which is just extremely hot and dense, called a white dwarf in the center. Eventually, it will cool to becoming a black dwarf, but there's been yet to be enough time go by to allow that to happen. So quite cool, really. It's just a theory that they'll get to that stage. So the white dwarf itself is actually prohibited from collapsing any more by something that can't really be explained by normal mechanics and what we call Newtonian mechanics. It's actually prevented by something called electron degeneracy pressure, which is a quantum thing. The electrons are stopped from getting any closer together because they need to occupy two of the same quantum state, and it's not possible for two electrons to occupy the same quantum state. So there's an amount of quantum pressure comes by from that, which is Pauli's exclusion principle, basically, which states that no two electrons on the same energy level can have the same spin, and you'd need to achieve that to make this neutron star collapse anymore. Quite cool, that. Right. Alternate 4, right, so we go back to 4. After a main sequence, we went to a red giant. Now we're going to look at alternate 4. Now, you can also become something called a red supergiant. So if you started as a really massive main sequence star, your fates are different. They have the capacity to repeat the process of gravity, crush, and then repeat. So instead of just leaving out their shells and then sort of fading away into nothing, that shell then came back and collapsed again and kicked off another layer of fusion. That happens over and over and over again, fusing heavier and heavier elements together and making layers of the stuff. It's quite cool. Eventually, in the most extreme cases of massive stars, they can make all the way up to iron, which is when they sort of give up the ghost, because iron's a very special element, being the top of the binding energy per nucleon graph. Basically, it's just very, very stable. You make anything bigger than iron, and it's less stable than iron. And you make anything slightly smaller than iron, and it's less stable than iron. So once you get to iron, trying to do something through a process of, like a spontaneous process like a star, it would need to put more energy in than it gets out of the process to get further on than iron. So it tends to just keep trying to get back to iron, and then it does this. It blows up. And that's called a supernova, which is a massively violent explosion caused by this violent fluctuation around iron, which is fusion, fission, fusion, fission. Like, eventually it becomes a supernova and it explodes like mad. And in that supernova, there's absolutely loads of energy to produce those higher value elements, which we actually have. Otherwise, if it wasn't a supernova, we wouldn't have any elements whatsoever bigger than iron. And that's what a supernova looks like, probably. I mean, no one's ever filmed one up close, obviously. After that, you can take two paths. So you could be a neutron star, right? The explosion from that surface pushes down on the core so much that it can overcome the electron degeneracy pressure, right? And produce something really interesting, and that is a star formed from purely neutron matter, right? So instead, all these charges that are desperately trying to be dealt with, they're pushed out of the way, and the whole thing turns into an uncharged thing, and it becomes a neutron star. Now, there'll be loads of electrons knocking about, but because of it all being a neutron, it basically becomes one massive atom, which is nuts, but it isn't. But it's becoming one massive atom in effect once it's done that. Now that neutron star is then prevented from further collapse by something called the neutron degeneracy pressure, which is produced by the strong nuclear force, the strong nuclear force. And if it doesn't stay a black hole, if it's got sufficient mass to overcome that strong nuclear force, neutron degeneracy pressure, and it collapses in on itself further than that, then things get really weird and we don't really understand them. But what we consider it to be is something called a black hole. And everyone loves black holes. It's like, oh, what do they do? Why are they infinite? Are they a wormhole? Are they real? Do they move? Are they closed? Do they have an event horizon? What does it mean? It's so much sci-fi has come out of black holes, but we don't really know anything about them, really. It's all theory and it's all dreamed up. But basically, the condition for a black hole is that light couldn't escape it, in that it would need an escape velocity greater than the speed of light. Anyway, quasars, pulsars, and blazars, some interesting phenomenon. A quasar consists of a supermassive black hole surrounded by an orbiting accretion disk of gas. A gas in the accretion disk falls towards the black hole and energy is released in the form of electromagnetic radiation. And it looks like that. Right. A pulsar, highly magnetized white dwarf or neutron star that is rotating, emits a beam of EM radiation on the axis of its rotation. Like that. And a blazar, very similar to a quasar, only key difference is it's more violent and more erratic. It sends extremely high energy gamma rays into space, as well as explosions of really high energy charged particles. There's no real distinction between it and a quasar, other than it's just a really violent version of it. And there's a picture of it. All of these pictures I took myself. I went in my ship. And then here are some other stellar phenomena that you should probably make yourself familiar with. Binary star systems, gamma ray bursts, circumbinary planets, black holes, eating stars, solar flares, and coronal mass ejections. All those things, look them up. Like, most of you will be familiar with what they are, but you can be asked questions that put the physics that you learn into these systems. Most commonly binary star systems, you'll see it in. I hope you're aware that a binary star system is two stars orbiting about their joint centre of mass. Right, so spectra, the first aspect of analysing starlight. So here's a cool thing. Each element gives off a characteristic spectrum of wavelengths, which is almost like a DNA profile, which is totally unique to it. These spectra can be obtained through looking at light from something like an excited source or a heated up source, which eventually, if you heat it up enough, starts to emit light. Now that will contain only certain wavelengths, and that certain wavelengths will be characteristic of the element that's doing the emission, and we call that an emission spectrum. The other one is we can look at light after it's been shone through a sample of an element, usually a vaporized sample, and look at the wavelengths that are missing from that light. And that is called an absorption spectra. And the pattern of these wavelengths, and I don't just mean the wavelengths, the pattern that they make, like are they bunched up here, are they spread out over there, those patterns are unique to that element. So here are some examples of what an emission spectra look like for different substances. So sodium, its emission spectra looks like this, with a couple of lines emitted with about 490, 495 nanometers wavelength, and then about 570, 80 ones, and 590-ish ones over here. You'll notice that none of them will have the same pattern. None of them have even got the same bits of pattern, and none of them have the same wavelengths exactly. Now emission spectra, each of those wavelengths, corresponds to a particular energy, according to the rule E equals hc over lambda, which is h is the Planck's constant, c is the speed of light, and lambda is the wavelength. Right? Now, each of these specific energies comes from a particular energy level transition that can be made by an electron in that element. Right, so it can fall from energy levels, or shells, as you might call them in chemistry, fall from these different energy levels to another energy level, and the difference in those energies corresponds exactly to the energy of the light that's emitted, which is, through that equation, corresponds to an exact wavelength. So their profile comes from their pattern of energy levels.